Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video investigates the linear correlation coefficient and how it can be used to establish linear correlation. Let's get started. To start off with, let's investigate where do we get the linear correlation coefficient from. And you can see this monstrosity behemoth of a calculation there in the center of your screen. This is what we use to calculate the value of R. Let me tell you something. If you're not yet joined the 21st century, this is motivation plenty to join the 21st century. Because I had to do these calculations by hand when I was in college. Oh my gosh, what a bear of a calculation. You don't want to do this by hand if you can get out of it. So yeah, let's join the 21st century. That said, let's look at each of the pieces of this so we can understand where it's coming from. Notice we've got sample size distributed throughout our calculation here. And then up top, we've got the sum of the x and y's. So a sum of x, y means you take each x value, multiply by its corresponding y value, and then add those products together. And then you're subtracting from that the product of the sum of the x's times the sum of the y's. So you take all the x's, add them together, take all the y's, add them together, then you take those two sums and multiply them by each other to get the second term in your difference there on the top of your fraction. Then down below, we've got the sum of x squared, which means you take all the x's, square them, and then add all those terms together to get the sum of x squared. And then we've got the sum of x quantity squared. Very different here, because that means you take all the x's, add them together, and then you square it. So note the parentheses are determining your order of operation. And then right next to it, we've got the same deal with our y values. So the sum of the y squared, sum of y quantity squared. So again, this is a huge calculation to be doing by hand. Let the computer do it for you if at all possible. Of course, the way R is calculated leads it to have some pretty unique properties. The first of which is that the value of R can't be greater than 1 or less than -1. So we're bounded within this range here. If all the values of either variable, the x or the y, are converted to a different scale, so let's say you've got distances measured in miles, and you want to convert to metric, so you convert all the miles into kilometers. Your value for R is not going to change. It stays exactly the same. Same thing if you swap the x and the y's. That's not going to change the value of R either. Now, the real, usefulness of R is the numerical value measures the strength of the linear relationship. Because it's bounded within this range of 1 to -1, the closer you are to those extremes, the stronger your linear correlation. The more you get to the middle, the more you have no correlation. So where you lie within that spectrum tells you the strength of your linear relationship. And also, because of the way R is calculated, it's very sensitive to outliers, because it's taking in position and it's putting it in several different places in your calculation. So one single outlier placed in just the right spot can have a drastic effect on the regression model that's produced from your data. So once we have our value for R, how do we know if good enough is good enough? Well, there's two ways to answer that question. And the first way involves using the table that you see there on the right. That's what we call our critical R value table. You have that in the insert to your textbook, but it's also listed in a number of other places. Usually your assignment problems will have a link that you can press, and it will bring up the table for you to use. And it's pretty simple to use. So essentially you take the R value from your data and you compare it with the corresponding R value from the table. So if you just deal with positive numbers here. So if you got a negative number, just get rid of the negative. Take the absolute value. We're only dealing with positive numbers here because only the positive numbers are listed on the table. So think of this like a pole vault jumper where you're trying to clear the bar. And the bar is the value you get from the table. If you are over that value, then you cleared the bar and you can conclude you have linear correlation. If you are equal to the bar, so you run smack dab into it, or you're not quite high enough, so you go underneath the bar, then that means you don't have enough support for linear correlation. The other way to get around this is with the p-value. So we're going to compare a p-value with a significance level, just like we did with hypothesis testing. And it's the same sort of criteria that applies in that regard as well. So if we can fit it inside alpha, then we have sufficient evidence. If we don't, then we don't have sufficient evidence. Sometimes students make the mistake of concluding that, well, if I don't have good enough evidence for linear correlation, then my variables are not related to each other. And that may not be true. There may be a nonlinear relationship at work, and you need to investigate some of those possibilities. And we'll talk about nonlinear regression in a future mini lecture. For right now, let's look at an example problem involving our linear correlation coefficient. So here we have shoe print length and height data for 10 randomly selected people, and we're going to use this data to answer these questions. What is the value of the correlation coefficient R? And are shoe print length and height linearly correlated at the 5% significance level? This data is found within our group inside StatCrunch. So if you want to load that data into StatCrunch and follow along inside StatCrunch, feel free. First, though, we need to check to make sure that our requirements have been met. First requirement is that we have a sample of paired data that's a simple random sample of quantitative data. And yes, that's what we have. Scatter plot shows the data points approximate a straight line pattern. Well, here's a scatter plot of our data. And while that may not look like a straight line, you're just looking for general trends. So if you imagine that this is actually following a really thick line, you might get away with saying, yeah, there's a moderate amount of correlation here. So look at the bounds for your data. Imagine the data is actually increasing through a band on the top and the bottom. So if you look at like a band like this, see how the data points are traveling inside that band. So if you were to approximate that with a line right through the middle of that band, you could say, yeah, it's more or less following that trend. Obviously, you've got some spread in the data, so you're not going to have more than a moderate amount of correlation, but yeah, there might be something there. Lastly, outliers known to be errors must be removed, and there doesn't seem to be any outliers here in our scatter plot, so we're going to call this good. If we use StatCrunch, once your data is in StatCrunch, go to Stat, Regression, Simple Linear, put in your X and Y columns, hit compute, and you come to find your R value is 0.847. Here's what the results window you get from StatCrunch. The R value is located right here at the top. So 0.847 when you round to 3 decimal places. To determine whether a linear correlation exists, we use our critical R value table. So here's our critical value for R. And notice here how we've got our sample size is 10. So we're going to look at the 10 row here for our sample size. And then our significance level, 5%. So we just go down this column here until we get to the row with the 10. And where those two meet up, that's where we're going to see our critical value for R, 0.632. So did we clear the bar? Well, we did, because our R value from our data is greater than that threshold value from the critical value table. Therefore, we conclude that these two variables are linearly correlated. Now, sometimes this is called a test statistic because we're comparing it with a critical value. It's not a true test statistic, as we'll learn in a future mini lecture. But alternatively, we could use the p-value to get the same result. So the p-value that you see here in the results table, take it from the slope row of your parameter estimates table, or you could take it alternatively from the ANOVA table. It's the same number there. And you compare that with the significance level, and you find that you're inside. Therefore, you're going to reject the null hypothesis, and there is sufficient evidence. And that brings us to the end of this mini lecture. I hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video.